So we are going to discuss some of the problems based on the central forces what we had discussed earlier, right? So note down one problem. So I hope you don't have any questions on the concepts. So if you don't have any concepts, then actually we can straight away start with the problems. So find the law of force towards the pole under which the following curves are described. Right, so in that actually, the first one is AU equal to e power n theta, and the second one is R equal to A into e power theta cot alpha, where alpha is a constant. So now actually, let us try to solve this problem. So find the law of force towards the pole under which the following curves are described. Now here actually, this is the equation of the orbit. Now actually, if this is the equation of the orbit, right, so we have to be finding out the law of force, which essentially means that the acceleration is proportional to some r power n. So this is what is called as the law of force. So law of force means, as we know earlier, so mass into acceleration will always leads to the force. Now the acceleration direction is nothing but the force direction. So if you are able to find out the p which is proportional to r power n, so this is what we call as the law of force or the law of acceleration. So in case of central acceleration, we always have the acceleration component only along the radius direction, no transverse directional component of the acceleration. Hence, the law of force will be always in the direction of the radius. Got it? So hence we are trying to find out the p value, which is a function of r power n. So that's what we are trying to find in case of law of force. Now here actually, so whether it is explicitly mentioned or not, so r can be treated as 1 by u. So this is the relation. If it is mentioned, that is fine, or else you can straight away take it, r is equal to 1 by u. Now here, the law of force actually we have already derived, that is, so u plus d square u by d theta square is equal to p by h square u square. So this is the law of force, right? So this is the equation of the central orbit. Now we are trying to find out the value of p in terms of r. For that actually, we already know that AU is equal to e power n theta. Now u value we got to know from that relation, and d square u by d theta square we should be finding it out. Now if I take the derivative of this, so in the case 1, so a times of du by d theta is equal to n times of e power n theta. So this is e power n theta, you can write as AU. So n times of AU. So this is a times of du by d theta. So du by d theta can be written as nu, or d square u by d theta square you can write as n times of du by d theta, and du by d theta you can write as nu. So n times of nu is equal to n square u. Now if you substitute this relation in the original relation, that is u plus d square u by d theta square is equal to p by h square u square. Now e power n theta, or just u plus, so this is n square u is equal to p by h square u square. So this is the fundamental relation. Now this u, if you take it out, 1 plus n square is equal to p by h square u cube, or p is directly proportional, or p is equal to 1 plus n square times of h square times u square, u cube, or p equal to 1 plus n square h square divided by r cube. Now this is p is directly proportional to 1 by r cube. So this is what we call as the law of force. Got it? So because actually 1, n and h all are constants. So there is only one single relation, p is inversely proportional to r cube, which we call as the law of force. Got it? So I hope you understood this concept. So essentially what we have taken the path of the particle and tried substituting in the differential equation, which is the orbit differential equation. From there actually we are trying to find out the relation for p. That's all. This is what we call as the law of force. Got it? So you can note down this. Okay. So note down. So can you try to solve the second one and tell me the law of force for the second one? R equal to a times of e power theta cot alpha, where a and alpha are the constants. So from here actually you can take it further. Okay. So what is the law of force in this case? So this will also, I think it will come as p is directly proportional to 1 by r cube itself. Okay. So note down one more. A particle moves in an ellipse. A particle in an ellipse under a force which is always directed towards its focus. Under a force which is always directed towards its focus. So in that actually, first one is find the law of force and the second one is the velocity at any point of its path. And the third one is the periodic time. Now, so in polar form, right? So polar form actually the equation of the ellipse by taking the pole as one of the focus. So you have to be aware of this equation. So this is being the major axis and this is the minor axis. So if this is the pole, then the semi-lattice rectum length is L. So this is the semi-lattice rectum length. So that is a perpendicular drawn to the major axis. So this height where it cuts the ellipse, this height is called as the semi-lattice rectum. So L is the semi-lattice rectum. Then the equation of the ellipse by taking this as the pole in the form of the polar equation is L by R equal to 1 plus E cos theta. So this is the polar equation of an ellipse. L by R is equal to 1 plus E cos theta, where E is the eccentricity and R is the radial length or the radius vector and L is the semi-latus rectum length. So E is equal to eccentricity. So based on this relation, can you try to find out the law of force for this? Anyone got the answer? See, this is being the pole. Now, any radial vector you can draw like this. So, this is the radial vector. So, this is R. And the angle between the radial vector and the initial line, which is called as the horizontal line, let us say this is theta. And then the equation of the ellipse is L by R is equal to 1 plus E cos theta. From this relation, so you can replace 1 by R equal to U. So, LU is equal to 1 plus E cos theta. And the equation of the orbit under central forces is given by, so U plus d square U by d theta square is equal to P by H square U square. This is the equation of the central orbit. Now from this actually U value we have got it from this straightforward relation. So then we can find out d square U by d theta square. So L times of du by d theta is equal to derivative of cos theta is minus sin theta and L times of d square U by d theta square is equal to minus E into derivative of sin theta is cos theta. So d square U by d theta square is equal to minus E by L times of cos theta. So here U can be treated as U is equal to 1 by L plus E cos theta by L. So if you replace in this equation both the values, so 1 by L plus E cos theta by L minus E by L cos theta is equal to P by H square U square. Now this E cos theta and E cos theta will cancel out and P is equal to H square U square into L. So U square can be treated as 1 by R square. So H square L divided by R square. So this is the acceleration. So H square L by R square is the acceleration what we can think of. Got it? So P is directly proportional to 1 by R square. This is also called as the inverse square law. Got it? You can note down this. So this is by L. In the denominator you are going to get it. H square by L R square. So this is actually usually treated as some constant mu by R square, where mu is equal to H square by L or H square is equal to mu L. So this is just a constant I have introduced in the place of H square by L, nothing more than that. Got it? Now how to find out the velocity? Now from this relation, h square equal to mu L, where mu is a constant. This is one relation we can use down the line. And mu L, so Lu is equal to 1 plus E cos theta. And the velocity relation for a central orbit is h square times of u square plus du by d theta whole square. This was proved yesterday. Right? So v square is equal to h square times of u square plus du by d theta whole square. Now those values we can put it. So we have got the u value here. So this is du by d theta. So L times of du by d theta is equal to derivative of, so E minus sin theta. So if you take du by d theta, so this is minus E by L times of sin theta. And here u is equal to 1 by L plus E by L cos theta. Now if you substitute both the values, this is equation number 1 and equation number 2 in this relation, then v square equal to h square times of 1 by L plus E cos theta by L whole square plus du by d theta is minus E by L sin theta whole square. So v square equal to h square times of 1 by L square plus 2 times of E cos theta by L square plus E by L whole square times cos square theta plus E by L times whole square sin square theta. So this value actually it becomes E square by L square. So this is h square by L square. If you take it out, then from this entire relation 1 plus 2E cos theta plus E square. So this is what is left over. Now 2E cos theta. So from this actually we can get u is equal to so u is equal to UL is equal to 1 plus E cos theta, or LU minus 1 is equal to E cos theta. So if you replace this value there, so 2 times of this h square by L square times 1 plus 2E cos theta can be written as 2 times of LU minus 2 plus E square. So this is, you can note down till this point, I am going to erase it. So from this relation, v square equal to h square by L square 2LU minus 1 minus E square. Yeah, so that's what is left over. Now this 1 minus E square, so for an ellipse, right, so standard relation is that is the semi-latus rectum length. So L should be equal to, so B square by A. So this is the semi-latus rectum for an ellipse. Semi-latus rectum, where A is the semi-major axis and B is the semi-minor axis. Now if this is B square by A is equal to L, so here actually, and A square is equal, or B square equal to A square into 1 minus E square is another relation. Now this is B square by A square is equal to 1 minus E square. Now here actually we have got 1 minus e square. Now we have some variable called L, which is the semi-lattice rectum. This L value you can replace with the term of b square by a. Then this can be treated as 1 minus e square equal to L by a, where L is the semi-lattice rectum and a is the semi-major axis and e is the eccentricity. So semi-lattice rectum length is b square by a, and the relation between b and a is b square is equal to a square times of 1 minus e square. This if you replace it here, then v square equal to h square by L square times 2Lu minus L by a. Now if you take L out and replace u with 1 by r, so this can be treated as v square equal to h square by L times of 2 by r minus 1 by a. So this is the relation of the velocity, and we have got h square is equal to mu L. There is another relation, or mu can be treated as h square by L, and this you can replace it here, v square equal to mu times of 2 by r minus 1 by a. So this is the relation of the velocity in case of central orbit under the force of inverse square law when it is moving in an elliptical orbit. Got it? Any questions on this? Any questions on this? So all these rules are actually as per the Kepler's laws. So because actually as per Kepler's laws, every particle moves in an elliptical orbit. So every planet tries to move in an elliptical orbit. So this is an elliptical orbit which is working under the central force. So in this case actually whatever the rules we are going to derive, it is nothing but the velocity of the earth. Also it is from the same principle, because earth rotates around the sun. The sun has one of the focus in an elliptical orbit. So this velocity relation or the acceleration relation is applied to any planet which is moving around the sun. Got it? Yeah. So now actually the third law of Kepler, what it says is t square by a cube or r cube equal to constant. This is the third law of the Kepler. Now we are going to prove in case of ellipse this is valid, where t is the revolution time around the sun and a is the semi-major axis length. So this relation we are going to prove it now. Done? Now the aerial velocity, actually we proved that dA by dt under the case of central orbit it is equal to h by 2, where h is the angular momentum. So even here also h square is equal to mu L, where here also h is the angular momentum. Now from this relation, suppose if it covers the entire area, that means a particle or the planet started from here, it tries to rotate one complete revolution. Let us say it took a time of the revolution time of t. So t is the revolution time. Then during the time period of t, it covered the entire area, right? So this entire area is nothing but the area of the ellipse. So area of the ellipse is pi times of AB, where A is the major axis and B is the minor axis. So pi times of AB is the total area it is covering. Now from this relation, so dA is equal to h by 2 times of dt. So h by 2 times of dt. Now if you integrate for the complete revolution, so now this can be treated as dA is equal to pi times of AB, and right side, so h by 2 times of the total time period is capital T. So pi AB is equal to h by 2, and then h value you can replace as square root of mu L. Now if you replace it here, pi AB is equal to square root of mu L by 2 times T. So our T equal to pi AB divided by square root of mu into square root 2 times of pi ab square root of mu into square root of L. But actually we have the relation of the semi-lattice rectum L is equal to b square by a. Now if you replace it here, 2 pi ab divided by root mu into L is b by root a. So this b will cancel out, and then 2 pi times of a power 3 by 2 divided by root mu. So this is the relation for the time period. So from this relation, t is directly proportional to a power 3 by 2, or t square is directly proportional to a power 3, or t square by a cube equal to constant. So this relation is valid for any planet. So this is the third law of Kepler. Got it? Any questions on this? Okay. Okay. So this relation, whatever I have derived, right? So this is valid for even for the ellipse or the hyperbola or the parabola also, because whatever the equation we have taken, which is given as L by R equal to 1 plus E cos theta. So this is the equation of a conic. In polar form. That means depending upon this E value, it will assume different shapes. If E is equal to 1, the same equation represents the parabola. If E equal to less than 1, the same equation represents an ellipse. And if E is greater than 1, the same equation will represent the hyperbola. Now, whatever the velocity relation we have derived, that is V square is equal to mu times of 1 by R minus 1 minus E square by A. So this is the relation, right? 2 by R. 2 by R times of 1 minus E square by A. So velocity of the particle moving in a conic, in a conic orbit. So this may be ellipse or parabola or hyperbola. So in any case, this is the same velocity. Now, if it is parabola, then E equal to 1. So this is the eccentricity is equal to 1. Then the velocity will be V square is equal to 2 mu by R. So this is the velocity. Suppose if E is greater than 1, then this is what we call as the hyperbola. So in case of hyperbola, E is greater than 1, you can bring this to the other side. So V square can be written as mu times of 2 by R plus E square minus 1 divided by A. So this is the velocity of the particle when it is moving in a hyperbolic path. Got it? So here actually this may not be a circular path, or this may not be a closed path at all. So when the particle is moving under any conic, so under the influence of the central acceleration, so this is the velocity. So that may be momentarily, it may not be periodic also. That is, suppose let us say if the particle is trying to move in a parabolic path like this. Now even in this case also, the particle will be attracted towards the sun. Suppose if the sun is located at this location, which is at the focus of the ellipse. So then actually, so this is the direction of the central acceleration. And if the particle is here, this is the direction of the central acceleration. If the particle is here, this is the direction of the central acceleration. Now when the particle is trying to move in this particular path under the influence of the central acceleration, where there is no angular acceleration, then this is undergoing with a velocity of given by v square is equal to 2 mu by r square. See, eccentricity means, see this, Arrhenius behavior is called eccentric, right? So even here also eccentricity means Arrhenius behavior. So that means it is deviation from the normal. So what is deviation? That is, suppose if a circle is there. Now a circle, this is the appropriate shape. Suppose if it is deviated like this, then this is eccentric to the circle. That means you are expecting that should be a circle, but in reality it's not a circle. It is a little deviation from the circle. So this is what we call as the eccentric nature. That means for circle, E value is 0. And here the E value is less than 1. And the eccentric nature of the hyperbola is E value greater than 1. And for an ellipse, actually this E value is equal to 1. So this is the deviation from the original shape. Got it? So a conic actually is characterized with this eccentricity, because from a cone, suppose actually if you have a cone shape, right? At different sections, actually if you try to cut it, you are going to get different kinds of shapes. In that, one is the circle, another is the ellipse, and another is the hyperbola, and there is the parabola. These four shapes actually you can get it from the same cone. So from the same cone, you are cutting in different ways and trying to get these four shapes. And all those four shapes are bounded by a relation with the eccentricity. So this eccentricity is nothing but, suppose graphically if you want me to explain, so this is, suppose if you take any particular shape like this, then this is one fixed point and this is one fixed line. Now depending upon this fixed point and this fixed line, let us take one random point. You calculate the distance between the fixed point and the random point, and you calculate the distance between this fixed point and this fixed line. Sorry, this random point and the fixed line. This distance, let us say this is P, S, and this is P, and this is M. Then SP by PM, and this is what is called the eccentricity. And this eccentricity, if E is equal to 1, then this is going to trace a parabola like this. So this is the kind of shape you are going to get it. In case if U is equal to 1, the locus of all the points which maintains SP by PM which is equal to 1, then that is going to be a parabola. Now, suppose if this E value is less than 0, what happens is, this shape, first you note down this, I am going to explain this conics also a little bit. So every conic actually can be defined from a fixed statement, that is, the locus of all the points which maintains a constant ratio from a fixed point and from a fixed line. So this is the fixed point and this is called as the focus, and this is the fixed line which we call as the directrix. Now from this point and from this line, if you try to trace all the points which maintains a same ratio of SP by PM, so this is what is called the eccentricity. So this is the master principle for all the kind of shapes. Maybe a circle, maybe a hyperbola, maybe an ellipse, maybe a parabola. For all the shapes actually this is the same master principle. From here only you can derive every other equation. So that is, from this relation only you can derive y square is equal to 4ax, and you can derive x square by a square plus y square by b square equal to 1. So this relation also you can derive, and x square by a square minus y square by b square equal to 1. This relation also you can derive, or even x square plus y square is equal to a square also you can derive. Got it? So all the relations you can derive from this single principle of SP by PM equal to E. So here this E value is the eccentricity. Now this distance and this distance, if you try to maintain equal values, then actually that is possible practically if you trace like this. So if you keep on moving like this, everywhere actually you will be able to find this distance and this distance as the equal values if you try to trace in this particular shape. Now suppose if this value is less than 1, that is, suppose if you take this, now this is the fixed point, and this is the fixed line. Now from this fixed point and this fixed line, let us consider a case E value is less than 1. If E value is less than 1, then what happens is it will try to trace like this till some extent. Now SP by PM, this value equal to E, which is less than 1. Now after certain distance, what happens is this SP by PM will try to go beyond 1. But actually you are putting the condition of E value less than 1. If it is going beyond 1, actually, so it will try to trace this way. So if it is 1, then this shape. If it is more than 1, it is trying to trace this particular shape. So this is what we call as the hyperbola. So this is parabola, this is hyperbola. This is also a parabola, but more or bigger parabola. So that's why it is a hyperbola. Now if it is less than 1, what happens is this value will try to trace this point. That means this distance and this distance, if you take it, this will maintain the same value E less than 1. Let us say if it is 0.7 or so, then actually here also it is 0.7 and here also it is 0.7. So everywhere actually, so it will try to maintain 0.7. For that actually you need to trace downward direction, but it should not go beyond. Why? Because if you are trying to trace this path, then actually this value will become more than this 1. Got it? Hence actually the path is possible to maintain this E value is less than 1. This is a closed shape like this for this fixed point and for this fixed line. And this shape we call as the ellipse. But surprisingly, for an ellipse, you have two different focus and two different directrix. That means the same shape, even I can trace by taking a focus here and by taking a directrix here. And from this relation, if I take a random point here and this distance, then SP by PM here also, it will be again less than 1. If you try to trace with this axis and this point, it will come in the shape like this. So it's a overlapping shape. That means we have two different directrix and two different focus which can trace the same shape. That's why ellipse will have two focus. That is from the central line, this is plus or minus AE. And this is x is equal to minus A by E, and this is at x is equal to plus A by E. These are the two different locations where you can try to trace the same shape from the left side values and the right side values. Got it? Understood, Vishal? So this is about a little on the conics. Note down one more. A particle describes the curve. A particle describes the curve R power n equal to A power n cos n theta. Under a force to the pole, find the law of force. Hence obtain the law of force under which a chordioid can be described. Fine. So can you try to solve this problem? Okay, so let me solve it. See this R power n is equal to A power n cos n theta. and this can be treated as 1 by u power n is equal to a power n into cos n theta, or a power n into u power n is equal to 1 by cos n theta is equal to secant n theta. Now if you take the derivative of it, a power n into u power n minus 1 into du by d theta is equal to derivative of secant theta is secant n theta tan n theta into n. So this n will cancel out, and then secant n theta can be written as a power n into u power n. So this is a power n into u power n into tan n theta. So this is a power n times of u power n by u into du by d theta. So a power n into u power n, this will cancel out. It implies du by d theta equal to u times of tan n theta. Now if you take the derivative of this again, d square u by d theta square u into secant square n theta into n plus tan n theta into du by d theta. So this is d square u by d theta square. So u into n into secant square n theta plus tan n theta into du by d theta can be treated as u times of tan n theta. U into n into secant square n theta plus u times of tan square n theta. So secant square can be treated as 1 plus tan square un 1 plus tan square n theta plus u times of tan square n theta. Un plus un plus 1 into tan square n theta. So this is d square u by d theta square. Now this value, if you substitute from the original relation of the central orbit, that is u plus d square u by d theta square is equal to p by h square u square. This is the equation of the central orbit. Now this equation of the central orbit, you can put the values of u and d square u by d theta square. First you note down this, I am going to erase it and write it. Now these values, if you substitute it, that is u plus d square u by d theta square, you can write as un plus u times of n plus 1 times tan square n theta. So u times of n plus 1, if you take it out, 1 plus tan square n theta will be left over. So this is equal to p by h square u square. Now this value u times of n plus 1 secant square n theta. Now secant square n theta from the given relation, that is, what is the relation? U power into a power n secant n theta. So this value you can put it here. So u times of n plus 1 into u power 2n a power 2n. So n plus 1 times of a power 2n into u power 2n plus 1, and this is equal to p by h square u square, or p can be written as h square times of n plus 1 times of a power 2n into u power 2n plus 3. So or p is equal to h square times of n plus 1 times of a power 2n times of 1 by r power 2n plus 3. So from this relation, the law of force can be written as 1 by r power 2n plus 3. So this is the law of force. Suppose if the particle is moving under this equation, which was derived from the original equation of, that is, r power n is equal to a power n into cos n theta. So this is the fundamental relation. From this relation we have written this, and from there actually we tried deriving this law of force. Now the extension of this problem, what he asked was is, so find the law of force in case of a cardioid. So the equation of the cardioid is, so r is equal to a times of 1 plus cos theta. This is the equation of the cardioid, right? So a cardioid where when theta is equal to 0, this is going to be 2a, and when theta is 90 degrees, this is going to be a. Now if you try to find out this being the pole, so this value is the maximum value which is happening at theta is equal to 0, and in polar coordinates the convention is the horizontal line is treated as the initial line. There is nothing like x-axis or the y-axis in case of polar. So horizontal line is usually treated as the initial line. From there we start measuring the angle theta. So from here, this is the shape actually we are trying to get it. So this is the semi-cardioid and this is the full cardioid. So this is the shape of the cardioid. Now this is the pole, and at any instant this is the radial vector. So this is the r value and this is the angle theta. So this is how actually when it is trying to move. Suppose if the angle is crossing more than 90 degrees, then actually, so this value is going to be a negative value, cos theta value. Hence this value is less than a, and exactly at theta is equal to 180 degrees, this value is 1 minus 1, which is equal to 0. Hence when we are trying to trace this radius vector exactly at theta is equal to 180 degrees, it is tracing to a value of 0. Hence this is coming and vanishing at the pole. Now if you keep on increase the value of theta from 180 degrees, then actually it will try to get the value of the radius, and this radius value is always positive. Keep that in mind. No negative value you can get it in case of a polar coordinate for the radius, because the radius is always treated as a length which is originated from 0 or the pole and it is going outward. So that's what is the radius convention. The angle can be 0 to 360 degrees. So depending upon the value of theta, you might get certain value of r that is always a positive value or 0 value. Got it? So this is the way actually you will try to trace the curve. Now actually when you keep on trace this value, when it is crosses more than 270 degrees, so this is the direction. So this is the value of the radius, you can get it at an angle of more than 270 degrees. And if it is coming out to 360 degrees, then actually this is the initial value it will try to trace. Got it? So this is the shape of the cardioid. Now when the particle is trying to move in this particular shape, so that is, it is coming like this and it is moving like this. It is coming like this and it is trying to move like this. Now when the particle is trying to move, then what will be the law of force? That is the question. So the law of force is actually, we have got this law of force. What it says is P is directly proportional to 1 by r power 2n plus 3. Now this relation, from this relation, if I take, let n equal to 1 by 2, then actually the equation what we can get it is r power 1 by 2 equal to a power 1 by 2 times of cos of theta by 2. Now if you square it on either side, then this value is r is equal to a times of cos square theta by 2. Now this value a times of cos square theta can be written as 1 plus cos theta by 2. So r is equal to a by 2 times of 1 plus cos theta. So this is some constant a. Now actually instead of a, this value is going to be a by 2. So this is some constant. That means the shape of this curve is again a cardioid like this, but rather than the length of 2a, now you might get the length of a. That's all. So the cardioid shape is going to be, now this is how the shape is. Now this length is a rather than a by 2, rather than 2a. So if it is a, you might get 2a, but if it is a by 2, then actually you will get double of that. That is A. So in this particular shape, that means in the relation whatever we have derived, which is the law of force for any random curve which is moving under the influence of r power n is equal to a power n cos n theta. From there, if n is equal to 1 by 2, then P is directly proportional to 1 by r power 2n plus 3 and n equal to 1 by 2. Here, P can be treated as 1 by r power 4. So this is the law of force. Got it? Understood? Any questions on this? Okay. Yeah. So that's all for today. So I'm going to take one more class where in pedal form, and so when the case of apes that happens, right? So those kind of problems actually I'm going to take it up in one more class. So there actually I'm going to close this session for the dynamics. Got it? Afterwards actually I will start with a different topic. Any questions on this? Yeah. So that's all for today. Yeah, thank you. Good night.